Welcome back. Hope you're doing well. We have been discussing the utility of matrices in order to work with what kind of transformation we might be working with. Something that may be full rank, meaning that it is the rank equal to the number of columns in the matrix, right? Or something with a particular null space, non-trivial null space, meaning it does not have full rank. We've been discussing these sorts of concepts all throughout, talking about matrices, rank, nullity, null space, column space, all of these different ways of figuring out aspects of each of these. But we've also used matrices to talk about bases of certain vector spaces. And we're going to come back and revisit that discussion a little bit today, namely in talking about what is known as a change of basis, going from one basis to another. Now, we're already familiar with some of the standard bases, that is, any of these things that are these subsets of our vector space that are linearly independent, one, and two, spanning. It needs to have both of these properties in order to be called a basis. We know also that any vector space has a basis, and that if there is any one finite basis, all bases for V are finite and have the same number of elements, and we call that the dimension of the vector space V. Here is one of those standard bases. This time for Rn, we have the one that is we have the vectors e sub I, where I ranges from 1 to n, and the way that you define the vector e sub I is that you put a 1 in the ith spot. So for example, for e2, the 1 goes in the second spot, and zeros go everywhere else. That forms the standard basis for Rn, and we can see that every vector can be written uniquely in this form of a linear combination of these ei vectors, because you can just take any vector x1 through xn, and then in the ith spot, if you have the scalar x sub I, well, that's the scalar for the standard basis element e sub I. Adding all those together, you get your coordinate back. Now, in general, bases do not have to be just the standard basis. If you have any other sort of basis for your vector space, then we also know any other vector could have a unique representation with respect to that basis. What we're going to do today is we're going to talk about these scalars and how to find these scalars given a specific basis. If we're looking for a vector that is a specific v, then what are the x1, x2 to xn? What are these scalars that have to go in front of these vectors for this basis? By the way, we're going to be calling these scalars the coordinates of the vector v with respect to the ordered basis. Ordered now, by the way, which is important since coordinates are ordered. Ordered basis v1, v2, all the way up to vn. And the way that we're going to be writing this whenever we have this sort of coordinate is we'll write x1 through xn. These are the scalars that are associated to each of the elements of this basis, v1 through vn. And we'll write those in the ordered list as a like a little subline to the coordinate that we're choosing. So an example of this is we could be looking at this in terms of abstract vector spaces. We don't have to be looking in terms of Rn. We could look into the vector space P2x. Remember, this is a vector space with dimension 3. You can get a standard basis for it in terms of the polynomials 1, x, and x squared. Now, any polynomial of degree 2 or less can be written in terms of the standard basis. For example, the polynomial x squared minus 3x in this space has coordinates equal to 0, -3, 1. Now, where do each of these numbers come from? What we have to do is make sure that we are writing this polynomial in terms of the elements of the standard basis. So I have to ask the question, what scalar do I have this multiplied times 1? Plus, what scalar is there multiplied times x? Plus, what scalar is there multiplied times x squared? Well, this is the polynomial x squared minus 3x. So we know the scalar for x squared is 1, and we know that the scalar for x is -3. Now, there's no constant term at all, so we know that the scalar for the constant polynomial is just going to be 0. Taking each of these scalars and putting them together into a coordinate gives us 0, -3, 1. That kind of lets us know how to be writing these coordinates. By the way, it is important that we had the basis given to us in this order, because that told us the order in which how to write our coordinates. If we had be given it in terms of x squared, x, and 1, we would have had to flip some coordinates around to get to the coordinate that we need. Now let's take a look at an n-dimensional vector space. Then it has a basis of n vectors, thanks to what we've been discussing before. And let's talk about how we can connect a n-dimensional vector space to the space Rn using what is known as the coordinate mapping. The coordinate mapping is going to be the way that you map a vector space V into the coordinates that you get in terms of the basis that you're working with. So say, for example, we know that we can write any vector at V in terms of coordinates if you are given a specific basis. right? And this is unique because we know that whenever you have a basis, any way of writing a vector as a linear combination can only be done uniquely, right? So this is a well-defined function that we have going on here. Remember, we said well-defined means one vector v cannot be mapped to two possible coordinates, because if it were, then our basis would actually be linearly dependent, which is a contradiction with the definition of basis. So we can do this mapping and make it well-defined, taking the vector v, writing it in terms of a linear combination in terms of its basis, and then picking out the coordinates, plucking those out, and writing them all as one tuple, putting all the coordinates and putting them together as an n tuple in this sort of set. Now, you can see that this is a well-defined function. In fact, this is a bijective function. This is a one-to-one correspondence. There's only one possible way for you to be able to write a specific vector, so that means that it's a well-defined function. If you have two different vectors, well, their coordinates are going to be different. There's no way in order to be able to get two separate coordinates and get the same vector. That's thanks to linear independence. And thanks to spanning, you also know that this is surjective. You could write this as any sort of particular form, right? Any other sort of scalars that you would like. This may not be quite spanning per se, but it does say whatever kind of numbers that I want to write inside of here, I'm always going to have a vector v that is that maps to this element inside of Rn. So I do get injectivity and surjectivity of this function. So this mapping is a one-to-one correspondence. And then what's more, it respects the linear operations. Remember, again, the linear operations are addition and scalar multiplication. If you add two vectors in V, well, what are the corresponding coordinates? You add the coordinates together. If you do a scalar multiple of a vector, you just have to scale the coordinates. So we are going to say that this is a theorem that tells us that every n-dimensional vector space is algebraically identical to Rn, and that is in terms of how they are as vector spaces. So what we might call this is a vector space isomorphism. You may be familiar with this term, depending on what you've seen as far as algebra in mathematics, maybe at an undergraduate level. A isomorphism you may know from the context of groups in this case, and you may not, and that might not be something that you know, but a vector space isomorphism essentially means that you get a bijection between two spaces such that that bijection respects addition and scalar multiplication. That is what's known as a vector space isomorphism. All right, so there's a pause right here. Here we go. Here's an example of what this means. Let's take the space of 2x2 matrices. We know that this has 4 basis elements. You can just put a 1 in each entry of your 2x2 matrix and zeros elsewhere. That is a basis when you collect all of those together, and there's 4 possible elements in there. That is algebraically identical to R4 as a vector space. That is given the ordered basis given here. Then you can get a mapping that is what is known again as the coordinate mapping from a matrix to the particular coordinates that work with it to get a vector space isomorphism between the two spaces. Note that we had to respect the order of our basis here. Here, for example, we saw that 1, 0, 0, 1 is the first element of our basis. So whenever we're writing A here in our first top left corner, then if we want to write that in terms of the basis element, we have to do A times 1, 0, 0, 0. That gives us our coordinate of A. Now, when we write with respect to the next coordinates, this one right here, 0, 0, 1, 0, this next basis element, that coordinate has to be the one that goes in the bottom left corner. So that's why we write a C next in our coordinate. That's the next thing that comes down. And if we continue this process all the way through, we're going to get B times 0, 1, 0, 0, and D times 0, 0, 0, 1. That's a way to write this matrix in terms of its linear combination of basis elements. So that is the reason behind why we have to order our coordinates in this way. But once we order our coordinates in this way, we get a vector space isomorphism between these two spaces, the space of matrices and of R4. Now, this is in terms of a vector space. Let me give a quick note here, because we know that we are only considering operations on the 2x2 matrices that make it a vector space, namely addition and scalar multiplication. Now, the 2x2 matrices are a very special kind of vector space because there's an additional element of structure on them that we are familiar with because we've used it a few times. Namely, it's okay to do matrix multiplication in this space. You can multiply 2x2 matrices, and that's closed, right, in that sort of space. But that is not what we mean when we say there's a vector space isomorphism. that is actually extra structure that does not make it a vector space. That makes it something more than a vector space. So we're only considering the operations that keep it a vector space, namely addition and scalar multiplication. R4 does not inherently have a matrix multiplication on it. It's 4 by 1 vectors. So there's no way to be able to multiply two of those vectors together, at least in a way that would make sense to us in the context of R4. So we're only considering these to be algebraically identical in the sense of the fact that these are vector spaces, namely that they have an addition and a scalar multiplication on them, not a vector multiplication, scalar multiplication. So the question is, how can we use this to find bases for subspaces of these more abstract vector spaces? Let's say, for example, we're working in the space of degree polynomial or polynomials with degree 3 or less. Let's take a look at this subspace here. Let's take the subspace that is spanned by the following polynomials. We have 1 minus 2x minus x cubed, 3x minus x squared, 1 plus x squared plus x to the third, and then 4 plus 7x plus x squared plus 2x to the third. So we have 4 polynomials here, and we know that the dimension of the polynomials is actually 4. Now, that doesn't mean that W is the entire space of P3. There could be some sort of linear dependence relation inside of here. Namely, one of these vectors could be redundant in taking the span. If that ever happens, well, we know that this actually could be something that's dimension 3, 2, or even 1 with this sort of span going on. But let's go ahead and see if we can figure this out. We've kind of already talked about how to do this, right? We've talked about how to take a collection, a subset of elements inside of a vector space, and pare it down to make it a basis. Let's see if we can apply that knowledge here. Let's let p sub I be the ith polynomial in this ordered list. So for example, let's let this be P1, let's let this be P2, let's let this be P3, and let's this be P4. Then we can write each p sub I as a coordinate in terms of its coordinate mapping in R4. Right, so we can write, for example, 1 minus 2x minus x cubed with respect to its standard basis. The standard basis for P3 is 1x, x squared, and x cubed. So you can see that the way that we have to write this as a coordinate is with respect to this standard basis, 1x, x squared, and x cubed. This is the coefficient for the constant term. This is the coefficient for the x term, coefficient for the x squared term, which does not exist, so it's 0. And then finally, the coefficient for the x cubed term. So this is how we could write each of these polynomials in terms of its coordinates. P2, we could do the same thing, get this to be 0, 3, -1, and 0, for example. Once we have all of those written down, we can write them as columns of a particular matrix. So you can see each column is written with respect to what the coordinates that belong to each of these spanning elements. Now, what we're going to do is start trying to pare this down. We're going to try and write this as a basis to figure out what to answer our question that's given here. Well, to pare it down as a basis, we remember that what we can do is one of two things. We could start by trying to find the column space of this, or at least try and figure out how to row reduce this matrix and then figure out what columns of this become pivot columns in the row reduced echelon form. So when I take my matrix A and I write it like this, I can go ahead and do row reduced echelon form to write it in this form. Okay, let's go ahead and see real quick, by the way, a neat trick for us to do row reduced echelon form. Okay, so here we are back for just a second at wolframalpha.com, and you can see that I've written this matrix in the way that Wolfram Alpha will accept it. I've taken each row of the matrix that I had on my screen just before and written it in these little curly braces, separating each row with a comma. I've gone through and written my entire 4x4 matrix in this command of RREF. Opening a parentheses up, I go through and write each row separated by a comma. And then after I'm finished with the 4 rows, I put a closed parenthesis. And then Wolfram Alpha says, okay, I can go through and row reduce this. The reason we're using it for this is that going through and doing the row operations for this might take some time. So instead, I'm just going to go ahead and try and plug it in, see what kind of result that I get. And I'm going to come back to my slides now to see what that sort of thing looks like. So here is our row reduced matrix. We have now that everything is either a pivot column or it's something that is associated to a free variable for us. Now, we know that these are not the particular columns that are associated to the basis, but instead, if we go back to the corresponding columns over here, the first, second, and third columns, we know that these columns and what these represent in terms of their elements in P3, we know that these are the basis elements for our subspace W. That's what we learned about in our previous videos. So we know that looking at all of this, that the dimension of the span of this subspace is actually 3, and that a basis can be given in terms of 1, 2, 3. The first 3 columns were pivot columns, so the first 3 polynomials given up here were form a basis for this subspace. In particular, we saw that this does not span the entire space. There is a linear combination. One of these elements, P4, namely, can be written as a linear combination of the other 3. So that's one way to go through and find the basis, but we've had another way to go through it to do it as well. Namely, we could go through and find a basis for the row space of A transpose. A, of course, we wrote these elements as columns. So if we write A transpose instead, you can notice that we've taken each of these elements and now the columns have become rows for this transpose. We can now go through and try and do reduced row echelon form for this because we remember from our video from earlier that doing row operations to everything inside of a matrix does not change the row space. It could change the column space. That's why we had to do something extra for our previous way of doing this, but it doesn't change the row space. So what does that mean here? I've got all of my elements inside that generate my subspace as rows now for this matrix. And once I go and do reduced row echelon form, again, using Wolfram Alpha, I get this matrix right here. So this basis now has coordinates equal to the rows of this matrix, since each vector corresponds to a row once we take the transpose like we did over here. So we can write each of these rows now as basis elements for the subspace W that we're looking at. Of course, we need to get these to be back into polynomials, but we can do this because each one of these columns now is associated to a particular element in my standard basis of the P3 space. So for example, the first row is 1, 0, 0, negative 1/3. That's this guy right here. So if I want to translate that back into a polynomial, I'll need to write that as 1 minus 1/3 x cubed. If I do that for each and every non-zero row, just like we talked about in the previous video, then we get another basis of W to be this, 1 minus 1/3 x cubed, x plus 1/3 x cubed, and finally x squared plus x cubed. So this is just another way to write the same subspace with a different basis. Instead of paring down the original set and putting it down, we've actually kind of made our basis look a lot nicer, easier to work with, and at least hopefully fewer terms that work better for us. Reduced row echelon form is very good about that. Let's go ahead and get comfortable with how change of coordinates work in R2. The reason that we're going to work in R2 is that in general abstract vector spaces, we're going to connect all of our notions of that back to R2 in order to be able to translate from one vector space to another. So let's start by trying to work with changes of coordinates in terms of R2. Now, what does this mean? That means that we are going to try and take things from a standard basis in R2 and start trying to say, okay, how would I write the coordinates for a standard vector in R2 in terms of a different basis? So for example, here in question 1, we have the vectors u1 and u2. u1 is the vector 3, 1. u2 is the vector 2, 1. These two things form a basis in R2. Let's see if we can find coordinates for the vector v, which is right now written as 7, 4. That's written in the standard basis with respect to the basis u1 and u2. Now remember that we are looking for values x prime and y prime here. These are the coordinates that we're looking for, such that our vector v can be written as x prime times the first vector plus y prime times the second vector. X prime and y prime make up the coordinates with respect to the basis of u1 and u2. Now, in particular, whenever you are looking at something in a standard basis, you're really looking at coordinates in terms of the standard basis. Here's how that looks. Whenever I write something in the standard basis, it looks like this. Here is E1, here is E2. We're really doing the same thing whenever we talk about something in terms of 7, 4. We're just saying, do a linear combination of the standard basis elements for R2, where you write 7 times the first one of those elements in the standard basis set, and 4 times the second element in the standard basis set. So that's where this sort of thing comes from. You can see that we are working with 7 vectors in the x direction because that is the first element in the standard basis set, which is 1, 0. And then we have 4 vectors going up in direction of the second basis element. That's for 0, 1. So whenever we write things in terms of the standard basis element, we mean coordinates in the exact same way as we would whenever we write it like this. Now, if we write it in terms of u1 and u2, we're just saying, okay, 1, 0 is no longer my first coordinate in my standard base or in my basis set. 0, 1 is no longer my second one. Instead, I have something that looks like this. My first element in my standard basis set is now 3, 1. And my second one is 2, 1. Notice that I had to take 2, 1 and actually make it go backwards for this one. 2, 1 actually would look a little bit like this, but I had to make it go backwards because we might end up having to go in the negative direction of some of these vectors as well. So the coordinates x, y, or x prime, y prime, as we've been calling them, correspond to how many of each vector in our basis it would take to add up to the vector v. So v is the thing in red, and then we have each of these other vectors that are added up, some linear combination of them. So this is of in terms of u2. And then we have in green our vectors u1 and some linear combination of them, such that when you add them all up, you get to our vector v. So geometrically, this is what we're trying to do here. So here's our question one more time. Let's go through and see if we can write this down. We want to write the vector 7, 4 in terms of the vectors u1 and u2, where u1 is just 3, 1. So I'm going to go ahead and write that down here. And then u2 is the vector 2, 1. So I'm going to go ahead and substitute that in there. Once I go through and say, okay, this vector on the left has to equal these 2 vectors on the right, the sum of these 2 vectors on the right, I'm going to get a system of equations, setting the first components equal and setting the second components equal. That gives me this system of equations, and I can just go through and solve that using substitution or elimination to try and figure out what x prime and y prime is. Notice, by the way, that x prime was indeed negative. We had to flip the direction of 3, 1 in order to make that work. My apologies. I noticed that on my previous slide, I said that this was 3, 1. That's a mistake. I'll write it in a different color. This one was actually for 2, 1. Not that it will matter too much. It's just good to kind of keep these things straight while we go through there. So this is that fact that 3, 1 had to be gone in the negative direction, and then we had to have 5 vectors going in the direction of the second vector, 2, 1. And if we add all of those things up together, we get our vector of 7, 4. Now, notice that in small cases like this, we could just use substitution and elimination. Essentially, that's a neat way to just try and solve for these values. But in cases where you have a lot of coordinates you need to solve for, so namely if you're working in something like R4 or R6, it's probably better to write this in terms of a matrix equation instead. And we'll talk about that in just a little bit. But let's see this in another example first. Let's see this in terms of question 2. Something's going to flip here from what we did in question 1. You remember in question 1, we said we wanted to write the vector 7, 4 in terms of some sort of combination of u1 and u2, where u1 and u2 form another basis for our space R2. Now let's flip that. Let's read question 2. The vectors u1 and u2, the same as before, form a basis for R2. Let's find the vector w, whose coordinates with respect to the basis u1 and u2 are 7, 4. To be clear, we're saying that we're trying to write the vector w such that w is equal to 7, 4 when written in terms of the basis u1 and u2. This is how you could see this written. Namely, it's the coordinates with respect to the basis, u1, u2, are 7, 4. That's how we could have this written. Okay, so what's changing here? We don't have this anymore. What happened here before was that 7, 4 was what we had in the standard basis elements, and we had to find out what were the actual coordinates in terms of our new basis. Now, 7 and 4, this is written in the new basis. And we need to try and figure out what the standard vector notation for that would be. How many times do I have to go cross x with the vector 1, 0? How many times do I have to go up by y, go up by the vector 0, 1? In order to do this, we need to try and find a new way to write it. And like our last question, we actually have that x prime is 7 and y prime equals 4. In the previous one, x was 7 and y was 4. In this one, the number of times you have to add the vector u1 together is 7. That's exactly what's meant by this term right here. The number of times you have to add u2 in this linear combination is 4. That's what's meant by this term right here. Now, if you add all of these together, you actually get the vector w in terms of the standard basis notation. So you just take 7 times u1 plus 4 times u2. That's exactly what's meant by the fact that this is x prime times u1. This is y prime times u2. X prime and y prime being the coordinates in our new basis. We want to go back to our old basis. All we have to do is multiply 7 times 3, 1, and 4 times 2, 1, and that gets us what the vector w is. It's 29 x and 29 in x and 11 in y. Think of it as this way, right? Pictorially, what we're doing is we are adding the elements of 3, 1. We're adding these vectors to each other 7 times. So we have 7 things right here, and then we have to do the same thing in terms of 2, 1 as well. So this is going to go well off the screen until we get to our vector 29, 11, and that's why we have such a big vector that's over here. 29, 11 is very, very big vector because we have to add so many of these vectors together in order to get to that point. Let's connect these two questions together into one picture. Given a vector v, let x, y be its standard coordinates, that is, with respect to e1 and e2. And let's let x prime, y prime, like we have been before, be its coordinates with respect to the basis u1 and u2. Let's try and find a relation between these two. Let's see if we can find an equation such that if I ever want to say, given any xy, I can find an x prime, y prime, or vice versa. Is there a way to find a linear relationship between these two? In question 1, what we were doing was when x was 7 and y is 4, we were setting up this equation. Now, we could write this in terms of its matrix equation. I said we would come back to this. Now is the time for us to do that. And once we get that matrix equation, we get something that looks like this. You can kind of see that what we're doing is we're setting all of the x components to be the things on the top row and all of the y components, the second components of these vectors, to be in the bottom row. Once you do this, this is what you get. So here is our vector 3, 1. Here is our vector 2, 1. They are forming the columns of this coefficient matrix here. In question 2, on the other hand, we instead flipped the way that these things were written. Instead of x being 7 and y being 4, we were actually we were just plugging in x is 7, x prime is 7, y prime equals 4 into this equation right here. So we were giving something like this. So we were actually working with this equation. So in question 1, we had x and y given to us, and we were solving for x prime, y prime. In question 2, we had x prime and y prime given to us, and we were solving for x and y. I'm starting to think that we have the idea of how we can connect these two coordinates with each other now. I think it has to do with this matrix, this coefficient matrix right here. So we define this matrix to be what is known as the transition matrix, going from our new coordinate system to our old coordinate system. Our new coordinate system, because that's what we get to start with. We start with the matrix or the vector 7, 4. Once we multiply it times this transition matrix, we end up in the standard basis. That's where we end up. So that's why the order of how we're defining these things. It goes from this new to the old coordinate systems here. Now, let's see how we would write all of this out. Here's how I might write it out. By definition, the span of E1 and E2 is R2, as is the span of U1 and U2, just that both of these are bases for R2. Hence, for any x and y in the real numbers, that is for our standard coordinate system, there exists x prime and y prime in R, that's for our new coordinate system, such that you can write one of these with respect to the other. X E1 plus Y E2 equals X prime U1 plus Y prime U2, right? So for example, in our previous example, we had this being 7, 4, right? This was 7 times E1 plus 4 times E2. Now we can write both of these in terms of their matrix equations. You can see how these things get written in terms of their matrix form. Notice that the columns for E1 and E2, when put together, just form the identity matrix, 1, 0, 0, 1. But we have our transition matrix back over here on the right-hand side. So if we just say, okay, the identity matrix times any vector equals itself, then we get the linear relation that we're looking for. Namely, I can find the relation between xy and x prime, y prime to be a linear relation, a matrix equation, connecting these two tuples of points, starting from x prime, y prime, and going toward xy. So this is going from our new system to our old system, just like we defined our transition matrix to be. We did not have to do it in this direction, though. We did not have to do this in the direction of going from the new coordinate system to the old system because we could have switched places. It doesn't make sense to just say, okay, for any x, y, and r, there exists x prime and y prime in r such that this equation is 2. In fact, it should make sense that we should be able to go backwards with that too, not just for anything in the old system, getting us to elements in the new system. We should be able to go backwards too. If instead we said, for any elements of our new system, there exist elements in our old system such that this equation is true. Let's be more specific about what that means. Over here, we were solving for x and y. We could also have been solving for x prime and y prime. Do you remember how we can go and take this equation and have it solve for x prime, y prime instead? All that we have to do is multiply by the inverse of this matrix on both sides. If we do that, then we get this sort of equation. X prime, y prime equals some sort of matrix times xy. And indeed, if we go through and take the inverse of our transition matrix, then we're going to get another transition matrix. But this time, instead of it going from the new system to the old system, it's going to go from E1, E2 to U1, U2. It's going to go from the old system to the new system, the standard basis elements to the basis elements that we have defined for R2. Now, remember how you go through and find the inverse of a 2 by 2 matrix, right? What you do is you go through and you say you divide by the determinant of your matrix. I'll call it U for today. And then you write such that the diagonal elements are switched in their position, and then the off-diagonal elements have minus signs in front of them. This is for finding the inverse of the matrix U, which is given in this form, A, B, C, and D. So this is our equation for finding U inverse. Again, we divide by the determinant of the matrix, and then we switch the diagonal elements and we negate the off-diagonal elements for our matrix. So you can see, for example, if I take the determinant of this matrix, I get 3 minus 2, so that's 1. So I'm just dividing by 1. That's just going to be itself. So all I have to do is switch the diagonal elements and then negate the off-diagonal elements. And what that does is it gives me the transition matrix going from my standard basis to my new basis here. So in general, we can do this in more than just R2. We can do this in Rn. Let V be any vector written in the standard basis. And let's let U1 through Un be a basis for Rn that is kind of our new basis, right? So let's let x1 prime, x2 prime, all the way to xn prime be the coordinates of V with respect to this new basis, right? So what we would do is sometimes, to be clear, we would write that this is, there's a little subnotation here. We would write U1, U2, Un. As a subscript of this coordinate right here. So we might write it as a subscript there. Then we can go through and form a coordinate matrix for this system of equations that forms whenever you try and write one vector in terms of the other with respect to these two bases. If you do that, then here is your coordinate matrix. Remember, that's the way that you form this matrix is that you take the columns of U to be the coordinates of vectors U1 through Un with respect to how they're written in the standard basis. The matrix U is called the transition matrix from the new to the old system, coordinate system. And then U inverse is the transition matrix from the old system to the new system here. So U is important and U inverse is important. We'll be using both of these as we go throughout here. So it's just important to make sure we keep in mind which one of those two matrices do we need to use. Are we going to try to translate things from the new coordinate system to the old, or from the old coordinate system to the new? Let's see if we can apply that here in this question. What are the coordinates of the vector 1, 2, 3 with respect to the basis U1, U2, U3? Here U1 is 1, 1, 0, U2 is 0, 1, 1, and U3 is 1, 1, 1. What do you think? Are we translating the vector from the old coordinate system to the new coordinate system? That is, from the standard basis elements to the basis elements we've defined? Or is it flipped? Is X already written in the new basis elements, and we need to get it back into the standard basis elements? Reading through this question, I see that the vector x is just written alongside here. It's not written with respect to the basis elements U1, U2, U3. In fact, we are asked, what are the coordinates of this vector with respect to the basis U1, U2, U3? We are asked to translate into the new basis coordinate system. So we are asked to go from the old to the new. I can go back to my previous slide now and say, okay, which transition matrix do I need to go from the old to the new? Well, that should be U inverse. Here is our standard basis element, and we want it to go into the basis elements that we have defined. So we need to multiply our vector x by U inverse. You need to multiply x by U inverse in order to get this transition to take place. So what we do is we take x to be written in terms of, take x written in terms of this new basis element to be equal to the inverse of our transition matrix, as we discussed how it's formed in the last one. We just take each column to be one of these vectors here given in this order, take the inverse of that matrix, and finally multiply it times our vector x. So we need to find the inverse of this matrix. One way that we tend to do this a lot is we try and do elementary row operations on this matrix right here. Think of this as like an augmented matrix. You have a 3 by 3 matrix over here, which is the matrix U. And over here, you have the identity matrix. It should look something like this once it's all formed. You can see on the left-hand side of the dividing line, you have the matrix U. And on the right-hand side, you have the 3 by 3 identity matrix. Whatever that is, just make it the same size as whatever U is. Then, when you're making elementary row operations to turn U into the identity, it turns out you're turning the identity matrix on the right-hand side into U inverse. So this is all done by elementary row operations. It takes elementary row operations to get us from one side to the other. And if we go through and do all of that, we get to U inverse. You can check this yourself if you'd like. You can see here that in order for us to get to from this matrix for U into this matrix, what I would do first maybe is take the first row and subtract it from the second row. Okay, so that's going to give us a 0 in the second row first column right here. And it's also going to give us a 0 right here. That gets our second row to look a little bit like the identity matrix. So the row operations I might take are first take R2 and subtract it, subtract R1 from it, and get a matrix from that. And then after that, I think the next thing to do would be, now that you just have 0, 1, 0 as your second row, you could take that row and subtract it from R3. So you could take R3 and subtract our new R2 from it. These are the two row operations. You can check yourself to see that this is the array of numbers that you would get from that. At the end of the day, this does indeed become our U inverse after taking these steps. So this is the U inverse that we're looking for. So U inverse is this matrix, and U inverse times X, once I go through and write all that stuff down, is -1, 1, and 2. I wrote the transpose of this because it's actually, I accidentally wrote it as a row vector instead of a column vector. So we should be taking the transpose of this vector to get what this value is. So we know now that X written in terms of this new basis is going to be -1, 1, and 2 in terms of its coordinates. We know now how many of each, what scalar multiple of each vector we need to add together in order to get the vector 1, 2, 3. Okay. So this is the process of going through and doing change of basis in terms of Rn. Let's go ahead and see it in the general case. We said that we were going to be connecting everything back to Rn. Let's see how that sort of thing works. Let's let V be just a arbitrary vector space now, but let's make sure it's a finite dimensional vector space. Let's say it's of dimension n. What that does is it allows us to use the coordinate mapping that we were talking about earlier in this video to write a function going from V to Rn. In fact, it's a one-to-one correspondence. One-to-one correspondences are very nice because as we're about to need to take, we're about to need to go through and take inverses of these functions. We know bijective functions have inverses to them. So let's let V1 through Vn be one basis for V, and then let's take the coordinate mapping. Let's call that one G1. You can see here that this is kind of a little bit of a map that takes us from V to Rn here. And then let's take U1 through UN to be another basis for V, some other generic arbitrary basis for V. It doesn't have to even be the standard basis at this point. And let's let G2 be this mapping, the coordinate mapping from the vector space into Rn. Then if we compose G2 with G1 inverse, what we're going to get is this. Well, G1 is going from here to here, so G1 inverse is going to go backwards. It's going to go from Rn to V, So that's going to be the first function that we take. And then if we go and compose that with G2, notice that we're back in Rn again. So G2, G1 is a transformation of Rn into Rn. It's the same sort of thing. Both of these are bijective, hence the composition is bijective. So what you're going to get from this transformation is that it's going to be described by a transition matrix. X maps to U of X, where U is some sort of n by n matrix. So we have a transformation taking us from one side to the other in terms of Rn. Well, we've studied transformations of Rn already, so we know that we can go through and find this transition matrix going from one set of vectors to the other. The columns of U this time, though, are going to be coordinates of the vectors vk with respect to the ordered basis uk. So this is different because our previous transition matrices always started from a standard basis E1 through En. The reason we don't get to do that this time is that I don't know if V even has a standard basis. What is the standard basis for an arbitrary vector space? I don't know. Because of this, we need to be working with these in terms of their transition matrices. Before we get into all the nitty-gritty of that sort of stuff, though, namely working with something that is a non-standard basis, let's start with one that does have a standard basis. We know that the space of polynomials with degree less than or equal to 2 does have a standard basis, and that's given by Q1 through Q3 right here. Q1 equals 1, Q2 equals x, Q3 equals x squared. Let's see if we can find the transition matrix from P1, P2, and P3, which are 1, x plus 1, and quantity x plus 1 squared, respectively, to the standard basis for the vector space P2. All right, so we have our map here. This is P2 of x right here. We have a way of writing P2 in terms of coordinates in two different ways. One way of those is to write it in terms of R3, in terms of its standard coordinate mapping. Okay, that's going to be on this side right over here on the right-hand side. This is going to be for the standard mapping. So the standard mapping happens over here. This is the one where we map everything in terms of its coordinates. So like, for example, we might send the polynomial 1 plus x squared over here to the element 1, 1, 1, because this is the map that's done by the map going from the standard basis elements of R to Q, or Q rather from Q to R. And then from P2 and R3, we're going to be using P1, P2, and P3 to be talking about this. This is in terms of our non-standard mapping. So this is a little bit of the picture that we have going on here. So we want to reverse something coming from our basis, P1 through P3. We're going to reverse it coming all the way through to the standard mapping for these. So we're going to try and just talk about this in terms of the coordinates for each of these, because both of these, G1 and G2, are meant to be coordinate mappings of P2 going into R3. So here's how we can do this. Note that, first of all, Q sub 1 going to Q sub 3, this is the standard basis for the space that we're looking at. So it should be easy to write each P sub I in terms of Q sub I. Here's how we're going to do it. Well, P sub 1 is 1, so we know that we can write this in terms of the standard basis elements. We have the constant term is 1, the x term is 0, and the x squared term is 3. We can do the same thing for each of the other polynomials. P sub 2 is x plus 1, which can be written as 1 plus x. Writing that in terms of the standard basis elements gives us 1, 1, 0 in terms of the coordinates in the standard basis. And then finally, P3, once it's expanded, becomes 1 plus 2x plus x squared. And you can see how we have that written down here. So this is what we have to work with in this point. Well, what are we going to do with this? We're going to take each of these coordinates here and we'll just kind of like what we did in Rn, we're going to write them in terms of a transition matrix. We're writing every x in terms of what they are in terms of P, in terms of the standard basis elements. So if we go through and write each of these coordinates in terms of what they are in a coordinate matrix or a coefficient matrix, we should get this transition matrix right here. Let's take a look and make sure that we know how this works. Each of these vectors is given in terms of 1, 0, 0. So you can see that we have to write the first vector here, P1. P1 is written as the vector 1, 0, 0. So we had to write that as a column of this transition matrix. P2 is written in terms of 1, 1, 0. So we had to write that as the second column. And P3 was written in terms of 1, 2, and 1. That is the third column here. So let's make sure that we get the transition matrix right then. Let's go ahead and see how this works in a generic case. Well, first things first, just like we had before in terms of the real case, note that the span of P1 through P3 is our vector space, which is the same as the span of our standard basis elements. Both of these are bases for our space. So that means that whenever you take a linear combination of things inside of your first span, that needs to be equal to some linear combination of things in your standard span of the basis elements, span of the standard basis elements, better to say. So how is it that we connect these two things together? Well, if I want to figure out the coefficients of the constant term inside of this, that is, if I want to solve for B1, I need to be multiplying A1 times 1 plus A2 times 1 plus A3 times 1. That's because the constant part of each of these non-standard basis elements is 1 in each of these. That's what we found up here. So you can see as we go through and multiply through 1 times A1 plus 1 times A2 plus 1 times A3, once we do this multiplying there, we get something that is equal to B1, the constant term in this part. This is another way that we can verify that we have the right transition matrix here. We shouldn't be taking an inverse or anything like that. This is actually what we need. So if we go through and continue all on throughout this, we can get the x terms and x squared terms once we have some coordinate written in terms of A1, A2, and A3. And we can transform that into the standard coordinate setup, B1, B2, and B3. Okay, so this is how this sort of setup will be working here. This is a neat place for us to get started in terms of abstract vector spaces because we have a notion of a standard basis set in terms inside of P2 of X. But what if we weren't working with the standard basis set? Indeed, what if we were working with something a little bit more complicated? So here's a question that asks us to find the transition matrix from the basis V1 through V3. V1 is 1, 2, 3, V2 is 1, 0, 1, V3 is 1, 2, 1, to the basis 1, 1, 0, U2 is 0, 1, 1, and U3 is 1, 1, 1. So here's our picture one more time. We have a vector space V, which can be written in terms of R3 coordinates if we're looking at the vectors V. So G1 is this vector, and this is going to be the coordinate mapping for the vectors V1, V2, and V3. And then we have another way to write this in terms of R3. And this is going to be the coordinate mapping in terms of where we're trying to end up. We're trying to end up at the basis U1, U2, and U3. So this is the picture that we're looking at. This one's G1, this one's G2. Well, in order for me to get from this R3 to this R3, I need to be able to map G1 inverse through to G2. So the function I'm looking at, just like we were talking about before, is G2 composed to G1 inverse. Remember, we plug in G1 inverse first, right? And then whatever answer we get out of that function, we plug it in through to G2. Now, here's the thing. We have this one is everything written in terms of V1, V2, and V3. This one's written in terms of U1, U2, and U3. What if we did this? What if we made the connection in between each of these to be whatever these things are written in terms of the standard basis elements for R3? What if we had the thing in the middle being the connecting piece being just the standard basis element? Well, I think I can map the new coordinate system to the old coordinate system. Remember, we did this back in our previous little section of this presentation. Taking things from the new to the old coordinate system implied doing what? We had to take the transition matrix for this. Now, let's scroll back just real quick to help us remember this. I want to remember if we need to be taking the matrix U going from new to old, or if I need to be taking the matrix U inverse if I'm going from new to old. So I'm going to scroll back to my previous page to reference that. Here we are. If I'm going from the new set to the old set, I need to be working with the transition matrix U. Again, U is formed by taking the columns of each of these vectors here. So let's go ahead and keep that in mind as we move forward here. So here was our picture one more time. We know that we need G1 inverse to be kind of a matrix U1. U1 needs to be what this matrix is. And then if we describe going from the old matrix to the new matrix here, we need to be multiplying times the matrix U2 inverse, going from old to new there. So that is what we're going to attempt to do. We're going to let us try and translate V1, V2, V3 first into the standard basis, E1, E2, E3, and then translate that into the non-standard basis, should be saying here, non-standard basis, U1, U2, and U3. So let's let U1 be the first transition matrix, and then let's let U2 inverse be the transition matrix from the old to the new. So U1 can be formed, that is this matrix right over here. This one is U1, from taking the columns of everything in terms of V, where we're starting from. So 1, 2, 3 is the first column, 1, 0, 1 the second, 1, 2, 1 the third. And then we're going to need to take U2 inverse, U2 being the columns of everything written in terms of the basis I'm trying to end up in, 1, 1, 0, 0, 1, 1, and 1, 1, 1. But I'm going to need to take the inverse of that. So I go through and do a little sidebar and say, what was the inverse of that? Or how could I go through and find the inverse of that? And we should get something like this over here. So this is still U2 inverse U1. But if I multiply those together, that's me composing these two maps. So that's the transition matrix U that I'm looking for. This is the transition matrix of this transformation. So this is the transition matrix from our beginning matrix, V1, V2, V3, all the way into U1, U2, and U3. We had to take a little bit of a segue through the standard basis for R3 in order to do this, but now that we've done this, we don't need to worry about trying to pair like one side or the other does not have to be a standard basis anymore. We can now go from more complicated setups where we're trying to go from one non-standard basis to another non-standard basis by just comparing how everything works with the standard basis for Rn, where n is the dimension of the vector space that we're working in. So we've talked a lot about how we can do change of basis, starting from Rn and now working in any abstract vector space. But that'll do it for me today. Thank you so much. Have a wonderful day.